So my name's Bryce. I'm the program chair here, and I'm on the C++ standards committee. And we're going to talk about C++ 17. My catchphrase for this talk is it's an introduction to C++ 17 via inspiring examples. You guys will have to tell me whether you find the examples inspiring. I do, but it's just me. So a lot of people worked with me on this slide deck or developed similar material, which I then stole. It's all of these people right here. And there are links there if you want to go and look at all of their resources. There's a lot of good material that's been put out there about C++ 17. I see Tony is in the back there. He in particular is responsible for a good chunk of this. So the first time I gave this talk, it covered like 32 features and like 100 slides and took like an hour and a half. And now we've got 24 things I want to talk about here, which is down from 26 as it was last night. And we'll see how many we get through. I'm pretty confident we can at least get through all the language features and all the major library features. So it won't be a problem if we don't get to the end. But we're going to get there. This session's probably not ending on time. Yeah, so I'm just going to sort of dive right in. So let's start off with the destructuring problem. So how do we assign convenient names to the components of an object? So like, for example, if I have some point3D class and I want to use it somewhere where I just want to I don't want to do p.x and p.y and p.z everywhere. I just want to get some local names for the components here. Well, we don't really have a good way to do this today. And there's a bunch of different dimensions to this problem. Like you might want those to have a value semantics or a reference semantics. And there is one facility you can use for this somewhat. So in before C++ 17, we had this thing std_tie that works with tuple. So if instead of using my own struct, I wanted to put it into a tuple, I could go ahead and do std_tie of some variable of this tuple, and then it would act as if it was binding to these names. There's a number of problems with this. Because the variable names need to be separately declared before they are bound. So like, oops, you could do something like this, and you won't really get a warning for this, even though you've written the name twice here. That's sort of annoying. There's other problems, like if you want to have it by reference here, that's not really doable because these names need to be introduced and default initialized before they are tied to. And again, like with const, same problem. In general, this pattern doesn't work well when you're trying to destructure into types that aren't default constructible. And even types that might be default constructible, if redundant initialization might be expensive, could be annoying. So also, it doesn't work with your types, doesn't work with things like std_array, which it should. It's kind of annoying. So C++ 17, we have this feature called structured bindings. And what it does is it takes objects like my point3D or tuples and arrays, and it destructures them into a bunch of components. So the syntax is like this. You have auto and the I'll talk about that part in a moment. But you've got a list of names here, and then you have the object, and the object must be destructurable. And that means that it's sort of intuitive. It needs to be something where it's sort of struct-like. So it either has to be all non-static data members that must be public, must be direct members of the type, or members of the same public base class of the type. They can't be unions. Or if you want to adapt some existing type, you can write customization. You can write specializations of these customization points to make pretty much any type work with structured bindings. So the destructurable types in the standard library, some of the more useful ones, std_array, std_tuple, std_pair. And the auto here, so you do need to use auto here or some form of auto, but it uses the regular auto deduction rules. So you can put like auto, ampersand, auto, ampersand, ampersand, auto. I don't think you can do any of the pointers in Texas. That wouldn't make any sense. And likewise for const file type clarifiers. So there's a lot of cool stuff you can do with this. So like it makes dealing with maps a bit easier. So like here I've got this for loop, and I'm a range-based for loop over this map. And in the initializer here, I'm using a structured binding to take the pair of the map and go into a key value. Yeah?
Can I have one value as a mutable and the other one as a const?
don't think so. Not in the way that you're thinking of. If you engineered it properly so that the auto deduction worked that way, then yes. But I can't actually think of a way how I would do that.
Is it just the thing on the left of the brackets apply to every member of the content? Can I put const in front of it?
Yes, you can put const in front of it. It's more or less that. I don't want to get too far into how it actually functions. But the short answer is I don't think that you can do exactly what you want. It does sort of need to be something that's going to be uniform and applied to all the types. Yeah, so this is useful when you're dealing with maps, because like map gives you back this pair of key values that's kind of annoying. You just want to get a key and a value. So that's pretty nice. And so this brings us to our next C++17 feature. A number of these features are features that make dealing with maps really nice. I swear we did not just design C++17 to make std_map easier to use, though. All right, so let's say that I've got this find and update function here, where I want to go find this key, and if it's there, I want to go and update it, right? So it's kind of annoying that this iterator here has to live in this outer scope because I need it in the condition here, right? That I'm only accessing this variable it in this scope here, but I do need it for the condition, so I have to put it in the outer scope. So this isn't just, it's not just ugly, but as I'll show you in a moment, there's some cases where it's just really ugly and can be really annoying and can lead you to write bad code. So in C++17, we've made if and switch work just like for loops, where they can take an initializer. So here, instead of having this declaration of this variable here, I can put it before the condition in the if loop, and then a semicolon, and then the condition. And then this variable will be in scope in the if branch, in the if statements block scope. So it basically, it's like this to this. Yeah.
As you do this, will you name the features? Because the name of the feature is cut off on the projector.
Yes. So this is selection statements with initializers. And my apologies for that. I didn't want to try to play around with the projector 5 minutes before the talk. Yeah, so it's this, goes to this. Pretty straightforward. I don't want to say think of it as if it's just a macro mapping here, but it's more or less that. So the scoping of variables when you have if and else if, it takes a moment to think about it. But basically, whenever you have one of these initializers, it's in scope in all of the possible blocks that could be taken after the initializer. So here, x is introduced in this if statement. It's in scope here, here, and here. Y is here, so it's obviously not in scope right here, but it's in scope here and in here. All right. So let's say that I'm implementing some string pool class. So yeah.
Could I reuse x instead of y? Or would it get a compiler error?
I don't know. I don't know. You would probably get a shadowing warning. Yeah. I don't think you would get an error. Don't do that. That's a tough one. All right, so let's say I'm implementing some string pool class. So the idea here is I want this class where it's gonna cache my strings after I'm done with them, and then give them out to other people who need strings, so that I can avoid having to go to the system allocator. So I can just keep my memory local. I don't have to go and call into the OS and make more allocations. And I want this to work between multiple threads, right? Okay, so I'm just going to talk about this one function here, pop. And the idea here with pop is I'm going to tell pop, hey, I'd like to get a string with this capacity. Either find me one, or if you don't have one, then go ahead and allocate one. So it might look something like this. So I have some string variable here, then I enter this critical section where I go and check if the pool is empty. And if it's empty, I go ahead and take the back element. Pretty straightforward, right? But there's a problem here. So the problem is that I have this one if branch here for if I can find something in the pool. That's the actual critical section, is this right here. But then I have this other part right here where I'm actually doing the capacity, and this will both handle if the one that I got was the wrong capacity, and if I didn't get one and I need to create a string that has the right capacity. But I'm still holding this lock right here, and this is not a critical section. So before C++17, you'd need to do something like this, put more braces in your code to make this correct. I don't need more braces in my life, so you could also just do this with C++17. So this is like my favorite thing to do with the if initializers. I think they're really nice when you're working with lock guards, where the first thing you need to do in your critical section is check a condition, which is a pretty common pattern. And as I said, they're useful with maps. They are useful with maps. So this is here, like I'm doing this map.inplace on this key with this value. Get back the key value, or here I'm getting back an iterator bool pair, and I can just destructure it in the initializer here. In this case here is if the insertion failed, and then I can do some error thing and maybe like report what key was already in there. And then in the other case, I can go and do some callback function on the inserted element. All right, there's also the switch init. It basically works the same way. I'm not going to show you any example for that. There's some that I'll put in the slide deck afterwards, but it's the same basic idea. All right, we're going to talk about another C++ extension to if. So let's say that we're writing a variadic print function like this. So before C++17, the way that you would implement this is that you'd write like some base case overload, and then you'd write some recursive version here that goes and picks off the first element of the pack, and then processes it, and goes and processes the rest of them. Pretty straightforward. All right, so then in C++17, we can just use this new feature called if_const_expr to write this in one signature. So what we do here is we have just this same signature here, and we do the printing out of the first element, and then we do the recursion here with this if_const_expr. And what this does is when this condition is false, this statement here is not instantiated, and so the recursion stops, and it's all good. Otherwise, it would just like infinitely recurse on the parameter pack size. You would eventually need the termination case here. So this is if_const_expr. It's compile time conditional statements. So the condition must be a const_expr expression, of course. And the rule is that each statement is discarded if their branch is not taken. And discarded statements can use variables that are declared but not defined. And discarded statements and templates are not instantiated. All right? Pretty straightforward. So, oops. So as I said, when if const_expr here is false, this statement is not instantiated. The recursion stops there. So there's a number of places where this is useful. If you're writing, there's some Sphene cases where you can replace Sphene with this. So like if I'm implementing make unique here, before C++17, I need to handle two cases. The first case is the case where the T is constructible from the arguments here, and I can detect that with this trait. And in that case, I want to do T parentheses the arguments. I want to do a functional style cast construct it. But if it's not constructible, so this case here, then I want to do unicorn initialization, so with squiggly braces, right? So in C++17, you can just write this like this. So just one template here with an if_const_expr in the condition. It's quite nice. You don't have to write the condition twice, and you don't actually have to use Sphene. So another slightly more advanced example, no pun intended. So tag dispatching. So if you were to implement an algorithm like advance, you could use Sphene, or another approach you could use is tag dispatching here. So what tag dispatching is that I'm creating some type here within the template, and I'm creating an instantiation of a value of that type that depends on one of these parameters here, in this case the iterator category. And then I call some other template function which takes another parameter and which is overloaded so that it has multiple implementations, and it will dispatch the correct implementation depending on this dependent type that we've instantiated here. This is a pretty common idiom that's been used in C++. So in C++17, we can just write it like this. Just one function. We don't need any impl function, no tag. Well, you still need a tag here, but it's much cleaner. All right, another one here. So this is probably my favorite one. So let's say I've got some person struct here. that has some getter interface here, and I want to adapt this to work with structured bindings, but I can't modify the struct, so I need to write the free get template function. I can't write the member get template function or do anything particularly fancy. So before C++17, this might be one way that you'd write it. So you'd declare the function here, and then you do full specialization, right, for each one of the cases here, and then you get a compile error if you were out of bounds. C++17, you can just write this. So just write it with if const expert. Now, you might be wondering here, well, what about the out of bounds case? Well, in the out of bounds case here, none of these branches are taken, and auto gets deduced as void. And then it's trying to instantiate void reference, which you can't do, and so you'd get a compilation error. So I think that's pretty cool. All right. Yep.
Just assume it was some void function, not returning something, where you wouldn't deduce it from the missing return type. Could I have an else with a static assertion false?
A static assertion false. Yeah, and that was not taken. A static assertion
would have been taken if I was like 3.
I believe that if you have a static assert in the else branch that's not taken, that you'll be fine. Yeah, it would have to be a template function, of course. Sorry.
If you don't have an else, it will compile. Static assert false.
Yeah, you'd need to have the else. Yeah. Okay. So next up. So this is fold expressions. So let's say that we're writing a variadic function where we want to sum up all of the arguments, all the input arguments here, something like this. So writing this before C++17 would sort of look like something I've shown you guys before, right? So you need some base cases. You need a recursive case here. You need 2 base cases here because you need to handle both the initial value case and the single element case, right? So because you need to both terminate recursion, you need to handle the case where you have where you call it with just nothing. So in C++17, you can just write it like this. So ns plus ... plus 0. So this is a fold expression. So it's a new way to work with parameter packs. So fold expressions apply binary operators to parameter packs. There are 4 types of fold expressions here. They differ in the order in which the binary operator is applied and whether they take an explicit initial value. And I'll talk about that a little bit more in a couple slides. The parentheses around the fold expression are required for parsing reasons. And all binary operators are foldable. So this is a binary right fold over the plus operator. So what this means is we've provided an explicit sentinel value 0. And the operator is applied from right to left. So it does 17 plus 0 here, and then it does the result of that plus negative 42, et cetera, et cetera. So a Boolean AND function is a good example of a unary left fold. So it folds over the ampersand operator here. And so we want to do the opposite order here, because we want it to short circuit properly. But notice we don't have any sentinel value here. So what happens if I call it with nothing? Like, what does it do? What does it return? So it needs to return a bool, obviously, but does it return true? Does it return false? Well, for these operators, you can use them with unary folds. So Boolean AND, Boolean OR, and the comma operator. And it will be assumed that the sentinel value is these values on the right here. And for any operators not listed there, you can't use that type of fold expression. So here's another cool one that I like, which is a print function here. So this is a binary left fold over the left shift operator. The initial value is stood C out. Then I'm folding over the shift operator here. And then I've got my argument here. And then and that's all in the parentheses. So this all here is the fold expression. And then at the end here, I'm just putting out a new line. And then this one is pretty cool too, I think. So this is a fold expression for where I've got a function here, and I want to apply it to each one of the arguments of this parameter pack individually. So I've got this function call here, and what this is a unary right fold over the comma operator. And so each one of those returns a void, so it doesn't actually produce a value. But I like this one in particular. All right, so next up is class template deduction. So before C++17, we've had function template deduction to simplify the usage of function templates by allowing us to omit explicit template parameters when they can be deduced by the compiler from the function's arguments. We haven't had that sort of deduction for class templates, which can be annoying. Something like tuple or pair, especially when you're writing it with like functional style cast, it can get to be very verbose. And so we have facilities like make tuple and make pair to help simplify this, and which go and use function template deduction. In C++17, we've introduced class template deduction. So now it is possible for your class template parameters to be deduced from declarations, functional style casts, and one other thing that I'll show you in the next slide. So here it's just std tuple and then t, and it'll deduce it from the arguments to the constructor here. And then in the functional style cast, it would also work. And it can also be deduced from a new expression. So I don't know why you would want to new a tuple like this, but this was just the simplest example I could think of, so bear with me. So previously you would need to explicitly write the types out. Now they can be deduced in a new expression. And so this is really useful in a number of places like lock guard. This makes the array pattern a lot easier, right? You go from having to write like this, where you write the mutex type, to just saying like, hey, lock me that mutex. Cool. So as I said, there's three things from which class template deduction can occur. So declarations, functional style expressions, and new expressions. It is only performed if no template arguments are provided. So you cannot, unlike with template function deduction, you cannot specify some of the parameters and have some of them deduced. If you specify, like for here, if you do std tuple int and you've got like t01, this will not work. You need to either provide all of them or none of them. So there's some cases where class template deduction doesn't work as you may wish. So a facility has been added called user-defined deduction guides that allows you to control how class template deduction operates. So the syntax, and I'll show you in another slide, this is syntax best understood through examples, but it's you write the template name and then a list of parameters, and you could put a template beforehand to declare the parameters. And then you write what it should map to, what instantiation it should map to. So these don't have to be templates, but they can be. And they must be within the same scope, so namespace or enclosing class as the class template. So for example, vector. So std vector has in C++17 a deduction guide for its constructor that takes 2 iterators. Because consider this case right here. I've got this vector, and I've given it 2 iterators. And I've not given it any template arguments, so I need to deduce it here. Well, the compiler doesn't know like what we mean here, right? What we actually mean is, hey, figure out what the value type of that iterator is, and then that's the type of vector that you are. And so that's what this deduction guide does. Is it says, hey, when you've got when you have this constructor that takes 2 iterators, go ahead and you're a vector of the iterator traits of one of those iterators. Obviously, there's probably a Svine condition to make sure that those things are actually iterators. All right, and so as I said, deduction guides don't have to be templates. So like if I have some name class here, takes a first and a last name, and then it's instantiated for some string representation, I could just have a deduction guide like this that says that C-style char const stars should be std string views. And if you don't know what string view is, don't worry, we're going to get to that. So like here, if I do this name in with these 2 string literals, this will become a name string view. But if I give it in here 2 std strings, it'll just become a name std string. All right, so next up, we're going to talk about another sort of deduction-ish feature. So auto non-type template parameters is the best formal-ish name we've come up with, but I like to call the feature template auto. So before C++17, obviously, it std integral constant, which is basically what I have on this slide here. It's one of our fundamental metaprogramming primitives. We use it to express compile time values. So you write like, hey, I have this int constant here, or I have a char or whatever, and this is how we do a lot of our metaprogramming. But this is kind of verbose. Like modern C++, we expect to have the capability to express a value and have its type be deduced. So in C++ 17, you can now have auto as a template parameter, and auto indicates a non-type template parameter that is deduced, not a type template parameter. So like here, that's my constant. Now it just takes one parameter. And so now I don't have to write the types. And if I'm passing it in like something like a function or even a lambda, I don't have to write it twice, which is really convenient. I can just write it once, it'll be deduced. So template auto uses the regular auto deduction rules. So auto, const, auto, ampersand, combinations of those, auto star, etc. Now, one thing to note is that it is heterogeneous. So it can be variadic. So like if I'm writing a sequence here, I can do auto dot 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 of elements of the sequence. And this is very cool. This sort of gives us a capability we didn't previously had. So like the integer sequence that we're familiar with in the standard library, it just really works like one class of types. But now we can write a more general sequence that will work with heterogeneous types, sort of a compile time tuple sort of thing here. Like this last one here, it's a sequence of int, char, and bool.
Bryce,
Yeah.
can you mix types in that sequence? Can you put ints in?
You cannot. Yeah, it's something that I've also wanted, but unfortunately no. So the question was the question I just answered was before that one was do they all, can you put types in there? And no, they all have to be non-types. And then your question was, do they have to be built-in types? The answer is no. They have to be anything that meets that can be a non-type template parameter. So I don't have the list offhand, but types that are literal types or trivial, that are sort of trivialish types. So like tag types would work. I'm hesitant to try to list the requirements off the top of my head, but it's not limited to built-in types. It is limited to anything that you could. Okay, all right. So actually, here's an example of where you'd use it with a non-built-in type. So a library that I work on has a representation of a multiple dimensions for a multi-dimensional array, where we want to be able to express both dynamic dimensions, so dimensions that we won't know until runtime, and static dimensions that we know at compile time. So previously, to make this work, we had to do hacks like just pick a magic value, like -1, and use that as the indicator that this particular dimension, we're not going to know it until runtime. But now in C++ 17, I can just write a tag type here and get the same effect, but without having to steal a value from whatever the homogeneous type of my parameter pack is. So speaking of metaprogramming, and this particular example, I want to talk about another C++ 17 feature, inline variables. So probably anybody who's done metaprogramming has seen a lot of this pattern where you need to put some context for values in your header-only libraries. In C++ 17, we've added support for inline variables that work like inline functions. So now you don't have to deal with all of the baggage that comes with putting a global variable in a header. So let me show you, well, let me go to the synopsis. So variables can now be inline just like functions. They may be defined in more than one translation unit as long as the definitions are identical. The definitions must be present in a translation unit that accesses an inline variable. And an inline variable can have external linkage, so like not static, and it must be declared inline, but it must be declared inline in every translation unit and it has to have the same address in every translation unit. A static context member variable is implicitly inline in C++ 17. So like if I have this like extern stoichiometric bool that I have in some header somewhere, it indicates that some part of my system's ready. Before C++ 17, you had to initialize it in the source file. Now you don't have to do that. You can just put it in the header and just leave it there. Same thing for if you have it as a static member, data member of a function. Okay. All right, so the next feature. So there's two sort of related features that help make lambdas usable in context per context. So prior to C++17, you couldn't really use lambdas in context per functions. And you couldn't really use them in context per context. So like here, I've got this lambda here, and I'd like to call it to get some value for this context per int I. I can't do that because the lambda's call operator is not context per. In C++17, you can mark it as context per, and then this works. But also, in C++17, the compiler just figures out if it can be context per or not. And so the context per is optional. You can put it there if you'd like, but if the function would be context per, the compiler will determine it. And so basically, this code will just work in C++17. But note that this does not make the lambda itself context per. This is the lambda call operator being context per. So if you want to have a context per lambda, that is now also supported. So a context per lambda is different in that it is, you can construct it in a context per context. You can copy it around because not only its call operator is context per, but also its constructors and its assignment operators. So Louis Dion is one of the people who championed this feature because he has a clever way of implementing tuples storage using context per lambdas. So the basic idea here is to have a series of these context per lambdas and to capture in the closure by value each one of the tuple arguments, and then the storage is the closure itself. And there's a ... here, which I've actually never seen from him, but that's where he says it's complicated but can be implemented. But so this is one of the things that you can do with context per lambdas now. So you can use them. They're usable now in context per context where they weren't really prior to C++17. All right, this is a very quick one. Static assert used to require you to give it two arguments. This first argument being the condition, second argument being a message. A lot of people have probably written code like this because they didn't want to write a message. Don't have to do that anymore. Now the second parameter is optional. That's all. So we're on guaranteed copy elision now. So before C++17, pretty much every compiler implemented return value optimization. But it hasn't been required. And because it hasn't been required, this means that you can't write a factory function that relies on return value optimization if the type that you're returning is non-movable. That even if the compiler is like, hey, I know I can RVO this, because it's not required, it needs to make sure that you actually have the constructor, so either a move or a copy constructor, that it would need if it couldn't RVO this. So this is no longer the case in C++17. You can now have something like this, like a grab lock function here that returns a non-movable type like lockguard. Pretty cool feature. So return value optimization is now mandatory. You can RVO non-movable types. Named return value optimization and other forms of copy elision are not mandatory. All right, next feature, another quick one. Nested namespaces. You can now declare namespaces nested like this. So syntax on the left, equal to the right. Pretty straightforward. Let me leave you guys here for a second. All right, next up. So this one is the last language feature we're going to talk about, which is good. We're doing pretty good on time, actually. So this is a new feature called hasInclude _ has include. It is a preprocessor predicate for header testing. So you would use it in like a hash if or a hash else if, etc. And what it does is you give it some header that you're thinking about including, and it tells you it's true if that file exists, and it's false if that header can't be found. So this can be useful for looking for optional dependencies, or like looking for something that used to be in experimental, but now is in C++17, so that you can work with both with older C++ compilers and newer C++ compilers. So it's a pretty nifty little feature. And speaking of string view, let's talk about string view. All right, so let's say we're writing this function here. So this first three function. So it takes some string and it returns back the first three characters of the string. So if we write it this way, it's kind of not great because we're forced to make a copy of this string here and to return a copy of the substring. And even if like we're going to use it like here in this case, like we don't need a copy. We're not modifying the return value here, right? It would be nice if we didn't have to make that copy. So in C++ 17, we have a thing called stood string view, which is a non-owning view into a string that lets you do this. So if you were to just change these interfaces to take string views and return string views, now you don't have to make it take a string view here. You could just return a string view here, but you should probably just take a string view in interfaces like this. And so what it will return is a string view is sort of the moral equivalent of a pointer plus size. So it's going to be something that's cheap to copy. It's just like this non-owning view. And then we don't have this copy here that we had in this prior example. So it's in this header string view. It's a non-owning view of a string, as I said. The interface is mostly the same as stood string. It has all of the find-ish functions, etc. It is, I'm going to say, in a number of places in the standard library that take strings today, also now take string views, but not all places. But that is something that will be corrected over time. So it doesn't ever allocate, doesn't ever new things. It doesn't own its contents. It's cheap, as I said. You should pass it around by value because it's like a pointer plus a size. You're not allowed to modify the underlying elements of the string, though. One of the reasons for this is that if you have a string view that you construct from like a car const star, you would not want to modify the terminating character. That would be bad. That would lead to bugs in your code. So this is a sort of read-only view of some type of string. So like here, this is using it with regex to implement a split function. So I want to like split up some string based on some token. And if I'm writing it with string, what I'm going to get back here is like a vector of strings. Like that's not great. I don't want to like create a bunch of new little strings. If you do it with string view, you get back a vector of string views. So a vector just views into the original input string that you gave it. That's nice. And so this is also useful for simplifying your string-related interfaces. So like let's say I have this function toInt. Its purpose is to take a string and to convert it into an int. So previously maybe I had like interfaces that looked like this. I had like a stood string constant, a car const star API, and then like one for my string. Well, with this string view, you can just make that the interface type that you use. And then like you can make your string convertible to that, and whatever other third-party strings you need to use can be just converted to that string view. It's not true for all interfaces that you're going to implement that are going to use strings, but there's a lot of them where you just need a read-only view. So I want to sort of expand on this example a little bit. So this toInt example here, like what do we do if we have an error here? Like if we can't convert the string to a integer. So there's a couple different options. So we could return a default constructed int on a parse error. Sounds like a great idea. We could throw on a parse error. We could return, sorry, that one should have an int there, and then like a bool, like an int by reference, and then a bool there, and return false on parse error. You could have like a unique pointer, and you could like go and allocate just cause, and return a null when you don't have it. So all these options I think are not as elegant as you might want. Even throwing is not as elegant as you might want, as there's a lot of people who might be using your interfaces who would not want to get an error reported via an exception. So in C++ 17, we have a thing called stood optional. What it is it's a nullable object wrapper. And it's a very convenient way to report errors from these sorts of interfaces. So it's in this header, include optional. It's a nullable object wrapper. It adds a null state to the value that it wraps. So it's sort of similar to this approach here, with the exception that it does not actually allocate memory. Yes, question?
To string view, actually, does it have a null state? Can I initialize it with a null pointer?
Yes, you can.
Okay, and how do I distinguish between empty string and null string?
I'm not sure I can. Let me get back to you on that. I'm not sure that I'm going to give you the correct answer off the top of my head. Yeah, does anybody here know? Is Tony still here? Anybody? All right. I'll find the answer to that for you later. Okay, std optional. So std optional, it sort of looks and acts and feels like a smart pointer, but it does not actually allocate memory. It just sort of has it in internal storage. I mean, if your type allocates memory, it will allocate memory, but it does not add another indirection of new allocation to your type. So it owns its contents. It should be cheap to copy if t is cheap to copy, and you should pass it, like if you pass t by reference, you should pass this by reference. If you pass t by value, you should pass this by value. And now it's not just about error handling, it's much more useful. So it's useful in a number of other contexts. And I'll show you an example or two of that. But let me show you a little bit of how you'd use it. So here, like I just do a std optional int. And note, of course, this int here, when I don't initialize an int like this, what do I get? Who knows? You could get anything. But for the std optional int, you know that it'll be default constructed here, so that you can declare it without initializing it, and it'll be in a valid state. And then I go and I do my horrible conversion mechanism of std string stream, and then like I just check for if it's succeeded, and if it's succeeded, I assign to the optional, and otherwise I just return the optional, which was just declared here and is in the default null state. So it's also useful for if I wanted to add a optional member to a class. So like previously, prior to C++17, a naive implementation of this might be like, if I'm implementing a person, and if like middle name, some people might not have a middle name, but some people we might not know that they have whether they have a middle name or not. So like we have incomplete data in our database, and we'd like to be able to distinguish in between those. But this is kind of tricky if we're going to use this as our predicate for whether the middle name is known. So if it's empty or not, then we can't distinguish between people whose middle name we know and people who have an unknown whose middle names we know and who they have no middle name, and people who we don't know whether they have a middle name or not. Sorry, that was not well described at all. I butchered that. It's okay though. So we could like add a bool to track this additional null state here, but that's kind of not great because like then you have these two things that have this invariant. It would be nice to encapsulate them. So I think std optional is a better approach there. And then you can ask whether or not the std optional, so just it's contextually convertible to bool, whether or not it's been filled in or not, distinct from whether or not the underlying thing, the string, is empty. And another use case for this is for optional parameters. So like if I have this slice function here with a start and an end, and like I want people to maybe provide one or both, but I'd be fine with people like providing. I want to have people to give people the option of only defaulting one of these, and so I don't want to like pick one where you have to like specify both. So you could do this with std optional, and then with this, it has a method value or, and so what value or does is that if it has the value, if it's in the valid state, and if it has a value, then it will give you back that value, and otherwise it will return the value that you passed into value or here. So like here I've got like I'm going to make a substring of some string here, and I do starts with value or, so it'll be 0 if this was in the null state, and otherwise it's going to be whatever that value was, etc. Yeah.
Is there also std none constant, like in boost optional? In boost optional, you have the boost ::none constant. Is there also such a constant with a new standard?
I don't know the answer for sure, but I think the answer is, sorry.
The answer is yes.
Okay. Okay. Thank you, David.
Okay, you could put it as default. Right?
Yeah. So the question was whether there is an equivalent of boost. It's num of boost num, and the answer is that it's std null opt. Yeah. All right. So next, we're going to talk about variant. And I've got the variant champion in the audience, of course. All right. So before C++17, writing a discriminated union was not easy. And actually, 7 years ago when I first came to this conference and talked on this stage, what I talked about was writing a discriminated union. So it's funny that I've like come back full circle. But yeah, it's not a fun process. Like if you want to do it using like a union, union is not great for this. You need to maintain the state, whatever state this thing is in, separately from the union. And so like that's very error prone. Like what if you keep adding things here and like you miss one of them and then like you're in trouble. And also like union is not great with things that are not built-in types. So if it's something with a user-defined constructor and destructor, I think maybe a non-trivial constructor and destructor, and you want to put it in a union, you basically need to use placement new and delete, and explicitly call the destructor, which is not super awesome. So in C++ 17, we have a really cool thing called std variant, which is a discriminated union designed for C++ and not for C, and it's a really powerful feature. So it's in variant, so discriminated union, as I said. The interface is similar to boost variant. There are distinctions from how std variant works and boost variant works. I don't want to really talk about those too much here. Access well, one of the common ways of accessing a variance value is through the visitor pattern. There are other ways of querying what state it's in and getting the value out, of course. So it doesn't do any heap allocations unless one of these objects that it contains does heap allocations. And it owns its contents. Whether you should pass it, whether you should copy it or pass it would depend on whether or not the things you're putting into it are expensive or cheap, and also sort of depends on like what state it's in when you're passing it around. So this is sort of one of the lengthier examples here, but I'm going to show a couple examples of how you can access variants here. So I've got this multiplier visitor that works for strings and ints, and then an array of 2 ints. And so using this std visit, I can give it an instance of my function object here, and it will go and it'll call the correct overload for whatever state the variant is currently in. All right, pretty straightforward. But it's kind of unfortunate that we have to like write a struct for this. It would be nice if we can do it in place. Well, we can. You can use if const expr and the sort of tag dispatching idiom I showed you earlier to do this with a lambda, with a generic lambda. So I have my generic lambda right here, and then inside of it I go and I figure out what type t is, and then I just have a bunch of if const exprs for all the different cases. It's kind of nifty. There's another thing that's sort of a preview of a feature that's probably going to come in C++ 20, which is I got this overloaded struct. What this thing does is basically you give it a bunch of lambdas, and then it creates a function object that has the overload set of all those lambdas. And it uses a C++ 17 feature that's not covered by any of my slides, but you can have a using declaration that takes a parameter that expands a parameter pack. So you can have a using declaration where you say, hey, I want to use the call operator of all of my variadic base classes here. And so then you would use it like this. So I would write, a bunch of lambdas, one for each case. And so then I can really sort of write the same pattern I had here of just writing like an overload set wherever I'm doing the visitation. It's kind of nice.
Bryce,
Yeah.
can you go to the previous slide, please?
Yeah.
With the if const expr.
Yeah.
We can't determine the type at compile time, right? If const expr is not a compile time evaluation, right?
So I'm not sure I understand the question.
So the variant can be in any one of the 3 types there. We need to check the if at runtime to know which one is the valid type. Am I understanding correctly?
So it will instantiate this internally in the place where visit is implemented. It will have each call to this, and at each call site of this generic lambda, it'll instantiate it with the correct type, and then there it will build sort of the right one in each place. Does that make sense? So I'm gonna have trouble repeating the question, so I think I'm gonna punt there. But it was sort of how does this work? Oh, and I forgot to mention this uses another feature here. This is when you're using the class template deduction for aggregate types, you normally need a deduction guide, and this was just the quickest way to write, the shortest way to write this example here. So this uses like 3 or 4 C++17 features. Variant's also useful for writing recursive data structures. For example, like a binary tree here. So like this is my binary tree. I've got like the branch here with left and right, and then I've got this std variant here for whether I'm a leaf or a branch. All right. So what if I need like a variant, but I don't know the types at compile time, or if like I don't like a heterogeneous vector. So we have this new facility in C++17 that adds. It's a generalized type erasure facility called any. It's somewhat similar to like a runtime type erased variant, but it's probably not the greatest way to think about it. I like to think about it as just a generalized type erasure facility. And so you can use it to do something like this, a std vector of std any. I can just put whatever I want in there. It's like I can put a string, a tuple, 42. I could put another std vector of std any. Pretty cool. So it's in this header any. It's type erasure. The objects have to be copyable. There's 4 main operations you can do with any. You can copy it. You can assign a value of some type t. You can ask it whether it contains a value of some type t. And you can retrieve a value of some type t from it with this anycast thing, which will throw an exception if you try to get a type out of it that it's not currently in that state. I don't believe there's a visitor mechanism for it because I can't really envision how that would look like. So you normally you need to sort of query it to get the state out of it. So it will return the type t. So it's a template member function that you have to explicitly say, hey, this is the type I want to get out of you. Yeah.
So I've seen someone who wrote a visitor for any that where when you call it, you have to specify all the types
Yeah.
that you handle.
Yeah. I think we should. It would be nice to have something like that. I think. I kind of like the visitor pattern, but I don't think we have it right now in the standard. And so std any, its type erasure, it will potentially allocate memory. It owns its contents. That one should be wrong. I should say it's potentially expensive because it allocates memory. But it is sort of dependent on how expensive copying your underlying thing is. But it will always need to allocate a new any when you copy it. And you should probably pass it by reference. All right, so now I'm going to talk about my favorite C++17 feature. It's parallel algorithms. It's my favorite because I have been sort of involved in this feature. So prior to C++17, we had some concurrency facilities, some threading facilities, but we haven't really had parallel programming facilities. So if you wanted to write something like just a parallel for loop that was also potentially vectorized, you'd have to use some other thing that's not part of the standard like OpenMP. So in C++17, we have parallel algorithms. So instead of writing this, you could just write std for each, just like the for each that you know today, except that it has an additional parameter that you could pass at the beginning, which is an execution policy. And so these two are roughly equivalent. It's also like if you want to do a parallel sort, hey, there's your parallel sort in C++17. All right, so because the algorithms live in both algorithm and numeric, and all the parallel overloads also live in both algorithm and numeric, the execution policies live in the execution header. So these new overloads, they take, as I said, this execution policy thing for most of the existing algorithms. And I'm going to explain what that is in the next slide. For now, I'm going to talk about some of the other places where the parallel algorithms differ from their non-parallel overloads. So the input iterator, any place where there's an input iterator requirement, in the parallel algorithms, it's been strengthened to forward iterator, and same for output iterator, I believe. The complexity guarantees are relaxed for some algorithms. There's both a general relaxation from any place where there's a complexity guarantee that is exact in the serial algorithms. We now say it's O of that exact guarantee. And there's also some other places where we further relaxed complexity guarantees where we did not, because we knew that there was not a parallel implementation that could meet that complexity guarantee. We also, yeah, question, yeah.
Are there some guarantees on the implementer, like some requirements on the implementer that you cannot create threads at that time, you have to be taken from thread pool? Something like that, some guarantees from that.
The question was, what are the restrictions on how the implementation of a backend? Let me cover that on the next slide. But the short answer is there are restrictions, but they're very general. That's a feature that's coming down the road. But I'm going to cover that in just a moment. So there's new algorithms that are designed for parallel programming. So reduced, inclusive scan, and exclusive scan are based on existing numeric algorithms, but they have weaker ordering guarantees. And then we have transform reduced, transform inclusive scan, and transform exclusive scan, which are combined algorithms. So transform reduced does a transformation and then feeds a pseudo sequence to a reduction. It's sort of like a more generalized map reduce. And yeah, let's get into what the execution policies are. So the execution policy describes the how of execution. So whether or not parallelisms are allowed, and sort of what type of restrictions must be respected by the underlying implementation. So how can you parallelize this? How can you screw around with my code while parallelizing it? And that's all that's in C++ 17. So it does not give you a way to specify where parallelism happens. That is coming in C++ 20. So executors are the thing that would describe where execution happens. So on a thread pool, current thread, GPU, etc. It's a feature that's in the pipeline. It's not in 17. Should be there in 20. So there's 3 execution policies in 17. Stood seek, stood par, and seek. I'm going to avoid reading you the formal definitions because I was thinking to myself as I was making this slide deck that's not useful to anybody but me. I just like it doesn't have a lot of value. I'm just going to tell you like what the TLDR is because I think that's better. If you want to look them up though, they're in the notes for the slide. So stood seek is just going to be serial execution. Now you might wonder why would you use this and not use just the non-parallel overload? Well, as I mentioned on this slide, there's some differences between how the parallel version and the serial and the non-parallel versions would work. Stood seek is a useful debugging tool because it won't give you parallel execution, but it would go through the same machinery. Also, the error handling is different for the serial algorithms and the parallel algorithms. Basically, for the parallel algorithms, if a uncaught exception escapes from one of your a function that you wrote, if you threw it an exception and it escaped from there into the parallel algorithms machinery, stood terminate gets called. And if you hate that, I am definitely the person to blame, and I am both sorry and not sorry at the same time. So stood par is most closely matches the SMPTE model. So parallelism, but not vectorization, because in SMPTE the vectorization is done by the hardware. So what this guarantees you is that there won't be anything that goes and tries to interleave your functions, and that the operations will be sequenced with respect to each other on each thread. This is basically like normal C++ rules, like the things that you would normally expect like C++ to do and compilers to do. Stood par on seek gives the compiler permission to do weird things that the compiler can't do today. In particular, it could, for for each, it could go and say, hey, I'm going to interleave multiple different invocations of the function that you've passed into for each, and interleave the execution of the individual steps of those functions. So it allows and gives permission for vectorization by the compiler, and it's a better match for it works for the SMPTE model. It works it's a better match for the SIMD model in particular. So like Intel GPUs. Which one you use, it should depend on what you're, not on the hardware that you're targeting. It should depend on what you can tolerate in your code. So don't match these to particular systems. Match these to what can I allow here? Is interleaving it fine? Is it not fine? And pick the execution policy accordingly. Yeah, I see a question in the back.
So if I'm used to doing rank order reductions in design,
if you're used to rank order reductions in MPI, yeah, so we should talk about that later. Yeah, I think we'd have to talk about that later. I don't think that's an execution policy question. Although with that said, you would definitely not want to use par unseek or unseek, I think. Although I think the interleaving that you'd get on a SIMD architecture from like a vectorizing compiler would largely always be sort of some ordering that's sort of no, actually I take that back. You should use std par, but I'm not certain that we have the algorithm that really gives you what you want. Std accumulate is completely ordered, but we don't have a parallel version of it, and std reduce allows arbitrary reordering. You might be able to do it with one of the scans though. So we should talk afterwards. All right. So I'm going to now talk about transform reduce briefly because I can't give a talk anymore without talking about transform reduce. It's my favorite function ever. So let's say that you want to do a dot product of two vectors. In C++17, you can do that, and you can do it in parallel with transform reduce. It's awesome and amazing. So transform reduce is sort of like an inner product. It's a little more generalized than inner product, though. So this is a version here that takes two sequences, the binary transform reduce. So it takes two binary operators, a binary reduction and a binary binary transformation. And for this overload, yeah.
Where's it getting the binary operation from?
They default to plus and multiplies. Yeah. And then, yeah, and so you can also write it in, so all of the new algorithms, the new parallel algorithms, they also have sequential forms. So like inner product, no, it's the other one that inner product doesn't have an overload for. But you can, if you just wanted to write like std transform, if you wanted to write this without the execution policy, you can do that. All right, next one, like let's say you want to do a vector norm. So I've just got one input here, and I want to do a vector norm over it. So I want to do, so the transformation I want to do is multiply the element by itself, and then the reduction is addition, and then I've just got a square root on top of it. So this is because there's no functional, there's no square function or square function object in the functional header. This one does not have defaulted operations. I'm sad about it, but maybe someday in the future. But so here I got transform reduce. I say the policy, got the input sequence. I have the initial reduction value, and then I've got the binary reduction op here, the addition, and then the unary transform op here, squaring. And this is parallel vector norm with C++17. All right. std the file system API. Okay, so prior to C++17, you had to use platform-specific APIs to access the file system. So here's what copying a file in a directory looks like on Windows. I should clarify, this is the code that Tony gave me. I don't know enough about Windows to know if this is right. I'm going to trust Tony on this, but like I'm slightly terrified by like they have like a copy file. Like that's nice, but like what is going on here? I don't want to know. I don't want to know. So C++17, we have a file system library that's pretty nice. It's based on Boost file system, and it's a portable way to access the file system. And I also think it has the benefit of having a pretty nice modern C++ API. So it lives in file system. It does have the unfortunate long namespace. So you will frequently see people in examples or in code do this namespace fs equals std : file system. Everywhere I'm going to talk about it, I'm going to do that. It's based on Boost file system, as I said. Its interface is primarily non-member functions that operate on path objects and on other objects like directory iterators, but path is sort of the main vocabulary type of the file system API. So it's file system path, and as you can see here, you can do things like the slash operator to concatenate a directory, etc., and it handles all the differences between the file system structure on Windows and POSIX systems. And then there's, for working with directories, there's directory entries and then directory iterators. And then there's a whole bunch of metadata types like file set status that sort of abstract away a platform-specific structures that have the same basic information. There's 4 major things you can do with the file system interface. You can create paths and manipulate paths in a platform agnostic way. You can iterate directories and you can recurse through directories, so you can explore the directory structure. You can query file and directory metadata, and you can create, remove, and modify files and directories and modify their metadata. So this is a function to display the contents of a directory that we're in. On the left here is the POSIX API implementation, and on the right here is the C++17 implementation where we're using directory iterators to go through it all, and then we're querying the metadata status as we go. So I think it's a much nicer API. All right, so next up is polymorphic allocators and memory resources. So the old memory allocator model can cause an explosion of instantiations of allocator-aware constructs with all these different allocator types here. So I've got, it's kind of unfortunate that if I'm going to use 4 different vectors with 4 different allocator types here, that I need separate instantiations of all of vector for this. And then also, if I'm going to use list 2, then I need, or if I'm going to use vector of double, then I would need another instantiation of both my allocators and of my containers that I'm using the allocators with. It's kind of not great. So in C++17, we have a polymorphic allocator and an abstract interface called memory resource that lets us, it's basically a type erased allocator, and then some the interface that the type erasure is done upon. So it's std : PMR. See, they were clever here. They picked the short namespace name. This was a good decision. So std : PMR : allocator of int here, and same thing. I can do the same thing with my slab allocator here that I had here, and just pass it in. And now my allocator doesn't need to necessarily know about the particular type, etc. So there's also a number. Let me go here. Yeah. So there's a number of standard memory resources, standard implementations of this interface. So there's the std PMR new delete resource. That's the global new and delete. There's an unsynchronized pool resource. It's just a thread unsafe memory pool. There's a thread safe memory pool. And then there's a monotonic buffer resource where the memory is only released when the resource goes out of scope. So if you've seen any of John Lakos's talks about allocators, a lot of this is based on his work and the allocator model that he's been pushing forward in the standard. And so there's also these aliases in the std : PMR namespace for pretty much all the STL constructs that are allocator aware. What the aliases do is std : PMR : vector is equivalent to this right here, just as a convenience. Okay, so aligned new. So prior to C++17, you could rely on new giving you properly aligned memory below a certain threshold. But if you needed memory aligned to some larger size, cache line size, maybe something even larger than that, like the size of a particular cache bank, or in fact some multiplier of a particular cache to avoid cache aliasing conflicts. All weird stuff I've had to do and regret, but it's a use case I would like to have supported. It wasn't really possible to do this in a standard way prior to C++17. You needed to drop down to a low-level API like the POSIX memline. Has anybody here used POSIX memline other than me? Yeah, it's not my favorite thing in the world. Yeah. So in C++17, this just kind of works magically. What it does is if you mark up your types with a line as, or you mark up a particular value or a particular object with a line as, say, this is what I want to align to, and then when you new it, the new will call into this new operator new that is allocator aware. And I know I just said the word new a couple times there, and probably bad choice of words, but we've added these overloads of operator new and operator delete that take a std align val t which is just some enum that indicates that it's an alignment value. And when you call new, there's this lookup procedure that will prefer sort of being backwards compatible, but if you've asked for alignment, it'll go and call the global allocator, assuming you don't have some class-specific allocator that you've written. So the lookup is like this. Allocations requiring an alignment that is not guaranteed by alignment unaware global new. The lookup order is class-specific and alignment aware, then class-specific and alignment unaware, and then global alignment aware new. So, yeah.
Does that work if you have nested align classes?
Haven't tried that one, actually. I think it should, but I'm not positive of the answer about that.
Isn't alignment pushed to a type if you have a base class or a member of the alignment?
Yeah, but I think the question is like if you had both the class and then the member had an alignment requirement, which is preferred, and I think the classes would be preferred, and if they were not compatible alignments, then you might have trouble. But yeah, I'm not sure. I'd have to get back to you on that.
There's times where you just want, maybe it's like the data block or something.
Yeah.
That needs to be page aligned and not actually
Yeah.
class metadata and stuff.
Yeah. Yeah, I'm not sure I'm not positive about the answer to that. Okay. Yeah.
Would that somehow also work with if you align the person here inside a stud vector? To use the stud vector as the mandate block instead.
Sorry, talk me through that again.
So if you use the aligners here instead of a raw C array, if you want to use the same alignment but through a stud vector.
So if your person struct is marked with a line as correctly here, then within stud vector, using the default stud allocator, it's going to call. I'm not sure if it's guaranteed that it'll call array new, but no, I think it would have to. Yeah, it's not just gonna call any other allocator. Yeah, so yes, it would just work with stud vector out of the box. Sorry, I just had to talk. I had to talk myself into it. Yeah, I mean that's part of the reason for the design. But one thing to keep in mind is that today you do in many cases get like alignment will be respected. It's just that above a certain threshold on platforms, you don't get that guarantee, and this only kicks in on those platforms and takes care of those cases. So don't freak out and like think like all your code has been like unaligned up until now. You may have been fine, but there have been some corner cases where it's not worked out. Yes.
This might be a special question, but is alignment also put to the type of the allocator right now?
Don't think so. The question was: is alignment associated with the type of the allocator?
Yeah, in the traits there's no information about alignment for an allocator.
Yeah. So allocators right now. I don't think we have alignment aware allocators. Right now we only have alignment aware new and delete, and alignment aware class specific new and delete. That could be a thing that we should probably have in the future, but I don't believe we have that right now. Yeah.
Talk about the aligned deletes, and they have to match up, I assume, right?
I have never met an aligned memory allocation API where you can't just call free, where like it needs to call a specific one. Okay. All right. The question is answered. So on Windows, if you can't just call the alignment unaware delete. You need to call into that specific API. Yeah, on POSIX, you don't have to do that. So, and that's where I do most of my stuff. All right. Okay, so now I'm going to talk about some improvements to the associative container APIs. So before C++17, when dealing with maps, when you want to, you want to insert something into a map, but there's a potential existing key, and you want to have very concrete behavior that you get for what happens with the existing key, and you want to get back information about whether the insertion failed or succeeded. It's not super easy to do this today. Within place, it gives you back the standard pair of iterator and bool with the bool indicating whether the operation succeeded or not. But if you're doing it with just operator bracket, you don't get back that iterator to where the element was found there, which you might want if you were like, hey, I didn't insert as I wanted to. And so you have no way right here you also have no way of knowing whether this succeeded or not. You have no way of knowing whether P was even moved from or not here, which is kind of troubling. So in C++ 17, we've added some new insertion operations to maps. So all 4 of the maps, map, multimap, unordered multimap. So there's try in place, which will fail if the insertion failed, and it will guarantee you that if this thing here that you tried to move in was not moved if the insertion failed. So whereas in place does not make such a guarantee. And it will give you back the same thing that in place gives you of an iterator, of a pair of iterator and bool indicating whether the operation is successful or not. And then there's this insert or assign, and it will insert this thing, and it'll overwrite the existing thing, and it will give you back the pair iterator bool. All right, we also have so there are these splicing and merging operations now in C++ 17. So the coolest one is merge. All the associative containers have this. So if I have 2 maps, M0, M1, I can just say m0.merge m1. And so this will copy from M1 to M0. I think it does take it, or in this case it would. I believe it does take it by r_value_ref as well, so that you could just give M1 to M0, and then it would move the nodes out of M1 into M0 instead of copying them over. And this won't overwrite existing keys. I have on my notes here to read you out the complexity guarantees, and I don't think that that's a thing that I'm going to do. I think if you want them, you can go look at them in my notes. So there's also this node-based extraction and insertion interface. So like if I have this thing here where I want to take something from one map, move it into another map, but I want to change the key. What I can do is I can do this source.extract here, and it'll give me back this node type. So all the associative containers now have an embedded typedef for a node type, and it meets some interface. I don't have a slide for that, I think, but you can go take a look at it on CPP reference. And then I get the node out of it, so that removes the node from this. And then I can go and say, hey, I want to change the key of that node, and then I want to go and insert it into this other map. This is pretty cool. All right, we're going to actually end on time, which is amazing. Super psyched about that. All right, special math special functions. So there was previously a separate international standard that contained this collection of what are known as the special functions in mathematics. They're basically very popular math functions, is sort of the easiest way to describe them. The name is based on, it depends on who you ask, but it goes back to a very old Fortran library called SpecFun from Netlib, from probably older than I am. But so there's all these functions. They're now going to be in the std namespace. We basically just merged this separate spec document that had them into C++ 17. And there's all of these ones, and then there's overloads for controlling the return types. I'm not going to get into these too much. This is super specialized area. They're based on, this library is based on Boost Math, though. If you're familiar with Boost Math, you may be familiar with these. All right, 2 more features, then we're done. So C++ 17 adds variable templates for all the type traits and metafunctions in the standard library. So previously, if you're using isIntegral, you just write std isIntegral t, then you'd have to do : value. So now you can just write std isIntegral _v, and that is a variable template alias to this. Fairly straightforward. So this is what they look like, just for people who have traits of their own and want to write them yourselves. Although I guess maybe you stick an inline before there. I'm not certain whether that would need to be whether that's implicit or not. Yeah, I think you need to put an inline in front of there. And they're all mostly in type traits. Yeah. All right. So let's say that we wanted to write an all-integral type trait. So it's a type trait that takes a parameter pack, and we want it to be true if all of the elements are integral and false otherwise. So this is something you might see, or you might see a pattern similar to this, maybe not in a trait, but just in Sphene conditions, when you've got some functions that work with variadic parameter packs. So you could, with C++17, do this with fold expressions. That is very cool. But this is not lazy. So the fold expression approach will instantiate t : value for every element of the pack. So it won't do short circuiting. And that's not desirable in a number of cases. So we have these Boolean logic metafunctions in C++17. So stood conjunction does the equivalent of this here. And here's the three that we have. We have conjunction, disjunction, and negation. Bool constant is just this alias we introduced because I couldn't get integral constant. So this is in C++17. The reason it's on this slide is because I couldn't get the slide to fit otherwise. So conjunction basically does the equivalent of this, but with short circuiting, etc., and etc. for negation here too. So they're just lazily evaluated Boolean logic metafunctions. They have the _t and _v aliases as well. All right, so this is all the things we talked about. I have a much larger table of all the things we didn't talk about, but I didn't have time to throw it in here. But I will put it in the slides a little bit later that were on the link that I showed you guys before. So we are how close are we to ending on time? 3?
7 minutes.
Okay, I can take some questions. People have questions. Yeah.
Structured bindings nest.
The question was, do structured bindings nest? The answer is they do not right now, but we believe it is a area that we could explore in the future. So we don't think there's anything that would prevent us from exploring that in the future. Yeah.
You know what the motivation was for calling those things conjunction and disjunction?
Because we couldn't use and, we couldn't use, oops.
And you're wrong.
Yeah, I don't know what the choice was, but I really want to find out who was responsible for it.
It was Lou. They just didn't like trailing underscore.
I mean, but there were better names. There were better names. It's a little too verbose. So yeah, the names are not great. Any other questions? Yeah, back there. Sorry, can you repeat that one more time?
Can std be constructible from movable but not copyable types?
So can standard any be constructed from?
Yeah, okay, so the question was, can standard any be constructed from movable but non-copyable types? I don't think it can because of the type erasure. I think it has to be copyable, even if you don't use it, even if you only move the any, I think that it's still going to instantiate the type erasure code that will require copy constructibility. I could be wrong about that, but I'm pretty sure it's a hard requirement on copyable, not uncopyable, and that move copyable is not good enough. All right. Any other questions? Yeah.
I want to know the constant expert lambda can be as a function parameter or function argument directly.
So the question: a const expert lambda, can you use the
As a function argument directly.
I'm not certain I understand that.
Use the context for lambda as a function argument.
Yes.
I don't. So to
Context for lambda and pass it as a function argument. Is that the question?
yeah, it's pass it as a function argument to another const expert function.
Yes. I want to know your example. The const expert should be front of the lambda, right?
Yeah.
And definition is like that. And sometimes I want to use it in place from your function.
Yeah. I'm sorry. I'm still not sure that I understand the use case though. I'm sorry.
I think what he's asking, like, if you do not give a name to your lambda,
yeah.
in place, how do you define a context for?
I'm gonna. Okay. Is that sort of what you're getting at? That if you're using it anonymously, how do you mark it as context spur? So I don't think you can mark the entire thing as context spur. In that case, you would only be able to mark the call operator as context spur. That's an interesting. That may be a weakness of the way the syntax works right now.
I think it's totally sufficient for the call operator to be context spur in that case. When you immediately invoke it and it's anonymous.
Yeah, but yeah. But what if you're passing? But okay, if he's saying if you're passing it into a function where you're going to copy the functor, that might not be great. I think you should talk to Louis Dion about this. That does seem like it's a problem. Yeah, it's not great. Yeah.
Is there stuff that didn't make it into C++ 17? Concepts, modules. What got pushed down the road?
I don't know that I can answer that question aside from saying. So the question was: is there stuff that didn't make it into C++ 17? The best answer is probably yes. There is a lot of stuff. There's multiple things that are in flight right now. We have about 6 or 7 TSs in flight right now. Concepts is in a TS. Modules is heading to a TS. Ranges is in PTTS. Networking is in PTDS. Coroutines is in PTTS. Executors is in very early stages of maybe being in a TS. Concurrency and parallelism are both about to do their next round of TS. I'm sure I'm forgetting some. We have a large quantity of things that are in flight right now, and there's other things that are in flight, but that are not in a TS or that are just directly headed for 20. So yeah, there's a lot of things coming up. I think 20 and 23 will probably land some set of larger changes that will have a broader impact. I hesitate to comment too much as to future direction, though. Yeah.
Is there stuff that was deprecated or is hotly debated for deprecation too?
There's a bunch of stuff was deprecated or removed in C++. So the question is, was there stuff that was deprecated or removed? And are we going to deprecate and remove more things in the future? So there was a bunch of stuff that was deprecated or removed in C++ 17. I have a slide on that, but it's not in this deck. I'll put it in this deck when I upload it. And I'm not going to do a good job of remembering off the top of my head what those things are. As for whether we're going to continue to do that, we certainly are, and the rate at which we are willing to do that is a question that comes up frequently in the committee, and many people have many different answers. I think, we're talking about doing this stud2 thing, and it means different things to different people. Some people see it as a way to fix mistakes of the past without having to satisfy the requirements of those who have a very high bar for backwards compatibility. And there's others who I think view stud2 as not sort of a self-contained thing where we redo everything, but just as a necessity because of basically the size of the overload resolution set of standard algorithms and other constructs. And there are viewpoints in the middle of that, of course. All right, I think 1 or 2 more questions, and then we're going to wrap it up. Yeah?
For the execution policies from the parallel algorithm, is there a policy which only allows vectorization but no parallelism?
Yeah, well, it's a stud on seek. Yeah, that's an interesting story. It would have been really nice if we could have had that in. I really wanted that, but Yeah, oh, sorry. The question was, why don't we have a policy that just does vectorization, a parallel execution policy that just does vectorization? Why is there only std_par that requests both parallelization and vectorization? There's no good excuse for this. I came into the process at a stage where it was probably too late to. So I've been working on parallel algorithm stuff for like the past year and a half, and at that point, the parallelism TS had these 3 execution policies, and it was unlikely we were going to be able to add an additional one when we merged it in. It is really unfortunate, because like that's my like primary use case. Like I don't want to I barely write parallel code. I just like write vector code. That's all I do. So yeah, sorry, it'll be coming. Yeah. One more question, last one. Yeah.
Follow up. I mean, if I use a parallel version, does it spawn threads, or how exactly does it work? Does it specify somehow?
So the question was, how does the parallel algorithms work? Does it spawn threads? What does it do? The answer is, it is sort of a task-based system. The best way to think about it is to think about it in terms of executors, to imagine that there is some implicit global executor. And what an executor does is an executor is a thing that creates work items, so tasks. And that is the degree to which it is specified what an executor does. One way that you could implement an executor is by spawning threads. I suspect that it is unlikely that any standard library will implement the parallel algorithms by spawning up individual threads for each task every time you call the parallel algorithms. But there's a wide range of options here, and the reason why why you get such a vague answer to this question is because this is a facility that's designed to work on a very wide range of hardware with a very wide range of options for parallelism. So this is designed to work on GPUs and CPUs and other types of accelerators as well. All right, last question, I swear. Yeah.
If the variety of the possible variants of the execution is so wide, why not create a custom policy?
So the question is, why don't we have like more customized policies for specific models? So right now we don't right now I think we imagine that there might be vendor specified policies, and we've gone out of our way to leave the door to make sure we don't bake in anything anything too specific to the execution policies. So like all the error handling differences, all the differences, everything is said it's for these execution policies, and otherwise it's implementation defined. So there's room for implementations to extend it. For users to extend it is a different. For users to write their own execution policies is a different story. And right now there's no interface for what an execution policy is. And in fact, what an execution policy is not an easy question to answer. Executors are the thing that are sort of designed to be customized by users. But I posit that executors and execution policies are and should remain separate things. That an execution policy describes restrictions, and it would be nice in the future if we had a way of writing those ourselves, but I can't imagine how we would do that. Because there's specific forward progress guarantee language in the standard for those execution policies, and I'm not sure how to create an interface where you could write what progress guarantees are made by what progress guarantees you're looking for specifically. I think that would be difficult, but maybe in the future. All right, thank you all.